Welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 2 from the May-June 2017 International A-Level Cambridge 9709 paper 4 variant 2. It's a mechanics paper. And here we have a question about a wire ABCD consisting of a straight part AB of length 5 meters and a part BCD, okay, in the shape of a semicircle of radius 6 meters and center O. The diameter BD of the semicircle is horizontal and AB is vertical. All right, so that's a right angle, it's vertical. A small ring is threaded onto the wire and slides along the wire. The ring starts from rest at A. The part AB of the wire is rough. Okay, so it's friction. The ring accelerates at a constant rate of 2.5 meters per second squared between A and B. Show that the speed of the ring as it reaches B is 5 meters per second. So it starts from here, it's going down at 0 meters per second. Okay, it ends here. We have to show that what the velocity at B is. We have to show that that's going to be 5. It's accelerating downwards with an acceleration of 2.5 meters per second squared. So we know it's acceleration, so that's fine. So we can just, I think, use Suvat here. We know, all right, so let's have a look. So we're taking it from A to B. It's going vertically down from A to B. So let's write down what we know in terms of Suvat. Okay, so we know S equals, as we know here, 5 meters. That's 5. U was 0. V is the velocity of B, what we have to find. A is 2.5. And T we don't know. So we have S, U, V, and A. So we can use V squared equals U squared plus 2AS. So the velocity at B squared is equal to U squared, which is 0 squared, plus 2 times A, which is 2.5, times S, which is 5. So we end up with the velocity at B squared is equal to 5 times 5, which is 25. Therefore, the velocity of B is going to be 5 meters per second, which is what we had to show. Okay, so there's the answer to question number part 1. Okay, so now we go to part 2. It says the part BCD of the wire is smooth, so no friction now. The mass of the ring, okay, the mass of the ring is 0.2 kilograms. So the mass is 0.2 kilograms of the ring, which is traveling through here. Find the speed of the ring at C, where angle BOC is 30 degrees. Okay, so it's going to be moving at this direction. All right, velocity at C, we've got to find that. Now, it was moving here at B at 5 meters per second going down. All right, now what we could do here, because it's changing direction, it's not going in a straight line. Now, the Suvat equations are the equations of constant acceleration in a straight line. Now, the direction is changing. Okay, so over here we cannot use the Suvat equations, but we can use the energy equations. So I'm going to think about the vertical height below C of B. So I'm thinking about the level B and C. So I'm going to draw a couple of lines out here so this is going to be level B and this is going to be level C. All right, so I've got my level B and C. Okay, so what do I know about this? Let me call this zero potential energy. Okay, at this level. Okay, I know that at this point it's going at 5 meters per second. Okay, and I know I need to find this height, the vertical height. Now I can use this little triangle here. This is like a triangle, right angle triangle. This is 30, this is 6, this is H. It's a right angle triangle. So we can say that the sine of 30 is equal to H over 6. Now the sine of 30 is equal to a half. So you end up with H equals 6 times a half, which is 3 meters. So I know that the distance between B and C is 3 meters. Okay, so I can use my conservation of energy. It's a smooth ring, so there's nothing apart from the weight, which is affecting. There's no external forces acting. So I can say that the kinetic energy of the system at B plus the potential energy of the system at B is going to be the same as the kinetic energy of the system at C plus the potential energy of the system at C, where that's the start, that's the end of the journey. So kinetic energy at B is going to be given by a half times, and remember, kinetic energy is a half mv squared. Potential energy is mgh, mass times g times h. So we got kinetic energy is a half times the mass, which is 0.2, times v, which is 5. So a half mv squared, a half 0.2 times 5 squared. The potential energy at B, its height is 3 meters. So you got the mass, which is 0.2, times g, which is 10, times the height, which is 3. And that's equal to the kinetic energy at C, which we have to find the velocity. So we know that it's a half times 0.2 times the velocity at C squared. That's what we have to find. And the potential energy at C is 0 because I called that 0 level in my calculations. So now I have an equation which I can use to solve for VC. So I have a half times 0.1 times 25, that's going to be 2.5. I'm going to have 0.2 times 10, which is 2, times 3, which is 6, that's going to be 6, equals a half times 0.1, 0.2, that's going to be 0.1 VC squared. So I end up with 8.5 equals, you can say 1 over 10 VC squared. 8.5 times 10 is 85. So I'm left with VC squared equals 85. So VC is equal to the square root of 85. Okay, so I can write that to 3SF. So I have the square root of 85, which gives us 9.22 meters per second. That's the velocity of C. Okay, now the speed at C. Okay, the speed at C. Not the velocity, the speed. Okay, so that's the speed at C, 9.22. The speed is 9.22 meters per second, not squared, meters per second. All right, now it says find the greatest speed of the ring. Now, of course, the greatest speed of the ring is going to be when it's, got the maximum kinetic energy, and that will be when it's furthest, like away vertically from the start point, which is from B. So it's going to be when it's exactly 6 meters below B. So we can do this in two ways. We could take, I think the safest way is to take from B to this lowest point. Okay, let's call this point X. So the safest thing is to go from B to X. We could go from C to X, but maybe the speed we worked out at C might not be correct, and then that will be error carried forward. We know that at this point it's going at 5 meters per second. All right. If we worked this out wrong, I could have gone from here and I could have said, okay, I know that that's 3 and that's another 3 meters. So I could have taken the speed here as 85 and worked out the speed there. But I think it's safer to go from the top because we know the speed there for sure is correct because they told us it. So we want to find the speed at X. We know that the distance between here and here, the vertical distance is 6 meters. Okay, so we can compare the total mechanical energy at B and X. So we know that the kinetic energy at B plus the kinetic energy at X, okay, sorry, plus the potential energy at B is equal to the kinetic energy at X plus the potential energy at X. Let's call this where the potential energy is equal to 0 at this level here. So at B, you're going to have a half times the mass, 0.2 times the speed, which is 5 squared, and the potential energy is going to be the mass times g times the height, which is 6. And that's equal to the kinetic energy at X, which is going to be a half times the mass times V at C at X squared. V at X squared, that's what we have to find. That's what we're asked to find here. There's a greatest speed of the ring, which will be at the lowest point here. And that's plus the potential energy here, which is 0, because we call this the 0 level. So when I sort this out, I should get my answer. Let me just sort this out. So we're going to have a half times 0.2, that's 0.1 times 5 squared, that's 2.5. And that's going to be 2 times 6, which is 12, equals, that's going to be 0.1 v squared. So that's 17.5 over 0.1 equals v squared. So v squared is equal to, it's like multiplying both by 10, so it's 175. So v is equal to the square root of 175, which gives us the square root of 175, which gives us 5 root 7, which is at 13.228. 13.228 goes on. So we can say here that the velocity at x, we can say the greatest speed, okay, the greatest speed is going to be 13.2 meters per second. Why would that be the greatest speed? Because that's where it's got the maximum kinetic energy. Okay, it's going to have the maximum kinetic energy when it's down here, as to compared to anywhere else along this journey. When it goes back up here, it's going to start having, it's going to gaining some potential energy. So the potential energy here is completely converted into kinetic energy by the time it comes there. So that's going to be where the maximum speed is. Okay, so there's your answer to part B of this question, and that completes this question here. Other questions from this particular paper, if I ever do answer them, I don't know what's happened here, that's gone up there. If I do ever answer them, they're going to be placed in this region over here. There's going to be a playlist for this paper, which will be over here in this area. Other questions from this topic, which is to do with, I guess, kinematics for just a little bit of part A, and the rest of it was about energy, work, energy, and power. So I'll put it under that same heading. And you can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.